In this lecture, we'll discuss climate change from the perspective of the physical, or sometimes called hard, sciences. Now, I can't compete with Neil deGrasse Tyson, so I won't try, but it's important to lay a foundation so we can build upon it later. First, what is climate? In any given location, climate is the weather conditions that prevail in an area in general and over a long period of time. By weather, I mean levels of temperature, precipitation, or rainfall, and seasonality, or the shifts in the first two components throughout the year. Let's take Denver as an example. Denver is a semi-arid climate characterized by low rainfall, about 15 inches per year, low humidity, i.e. not a lot of water in the atmosphere, and lots of sunshine. Denver's winters are normally dry and range from mild to moderately cold. Now let's contrast that with Monrovia, Liberia, often called the wettest capital in the world. Monrovia gets about 182 inches, or 15 feet, of rain per year. And because it's so close to the equator, it lacks the really large seasonal shifts in temperature places like Denver see. Weather is what's happening right now. As I write this lecture, it's 39 degrees and there's snow on the ground. But it would be silly to conclude that those are normal conditions for Denver in early September on the basis of just that experience. Having lived here for 8 years, I can tell you it's anomalous. It's probably the third or fourth earliest snow Denver has seen since the 1880s. The difference between climate and weather is why someone like Oklahoma Senator James Inhofe, who thinks, or at least claims to think, climate change is a hoax, can take a snowball onto the floor of the Senate and claim that climate change is a bunch of bunk.
In case we have forgotten, because we keep hearing that 2014 has been the warmest year on record, I asked the chair, you know what this is? It's a snowball, and that's just from outside here. So it's very, very cold out. Very unseasonal. So here, Mr. President, catch this.
He's mistaking weather for climate, or at least he's pretending to for political purposes. From time to time in this class, we'll be talking about weather and weather-related events, like cyclones and droughts. But for the most part, we'll be talking about climate. And there's no doubt the climate is changing around us. It's changing because of something called the greenhouse effect. The Earth is its own greenhouse. It is surrounded by an atmosphere that keeps warm air from escaping into space. In this case, the atmosphere is performing a similar role as the glass or plastic in the kind of greenhouse you might have at home, letting in the sun's short-wave energy and keeping in infrared waves, while allowing long-wave energy to escape. Now, please don't ask me too many questions about this part. If you do, I'll have to refer you to the physics department. The problem is that humans, and the animals humans raise to feed ourselves, are making that greenhouse thicker all the time, allowing less energy to escape back into space and trapping it on Earth. And just as a covered pot boils faster than one without a cover, we're heating up, and glaciers and polar ice caps are melting at unprecedented rates. We're doing this by emitting greenhouse gases, or gases that trap heat energy in the Earth's atmosphere. The big four are carbon dioxide, which is emitted during the burning of carbon-based materials including oil, natural gas, and plants; methane, which is emitted in fossil fuel mining and the farts, yes I said it, farts of ruminant animals like cattle; nitrous oxide, which is emitted by fertilizers, plastics manufacturing, and Vin Diesel. Yes! And finally, sulfur hexafluoride, which is emitted by the electric power industry. Now, you may be asking yourself, don't most of these things exist in nature? Yes, they do, but not in anywhere near the concentrations we see right now. Because scientists do awesome things and figured they could harvest prehistoric air from ice cores, we know that going back 400,000 years, we've never seen the amount of carbon in the atmosphere that we have now. We are in uncharted waters. And those uncharted waters arrived just around the turn of the 20th century. Why? To answer that question, we need to think about what else arrived in the last couple of centuries. And the answer is the Industrial and Transit Revolutions.
Industrial Revolution, 18th to 19th century. The economic developments of the 1800s saw the development of agrarian and handicraft economies in Europe and America transform into industrial urbanized ones. The term to describe this phenomenon would be known as the Industrial Revolution, and was first used by French writers, but made popular by English economic historian Arnold Toynbee. The Industrial Revolution was underpinned by the Agricultural Revolution. From the mid-18th century to the mid-19th century, agricultural production increased significantly. The huge increase in food output supported the expansion and sustained a large population and boosted trade. The increased use of machines over human or animal power in farming also meant that less farm workers were needed, and they could leave the land to industrial towns. Better metals and richer fuel also contributed to industrialization by creating the steam engine, an integral machine to industrialization which powered factories, locomotives, and ships. The new steam engines used coal and iron, both in their construction and as fuel, increasing demand for these resources. Roads, canals, and railways changed Britain dramatically, connecting Britain and allowing goods to be sent over long distances. Visually, the revolution was clear in the new industrial towns, with smoking factories dominating the skyline.
The Industrial Revolution was a turning point in human society, creating unprecedented wealth, spurring technological innovation and urbanization, and helping to foment democratization on an unprecedented scale. And it was a turning point that would, as much if not more so than warfare, spawn the international system as we know it today, for the IR nerds among you. But the Industrial Revolution ran on the burning of coal and later oil, two carbon-rich fossil fuels that are responsible for most of the warming we've experienced to date, to generate steam power and electricity. And this was, for the most part, a shockingly prosperous development. Between 1400 and 1750, the GDP per capita of the UK grew a grand total of 54%, or about 1/7% per year. Between 1750 and the year 2000, it grew 1,142%, or about 4.6% per year. That growth may have enriched a lot of fat cats, but it also turned rural peasants into a burgeoning, thriving urban middle class. The second big revolution was the transit revolution, the advent of personal transport based around the internal combustion engine. Now, this is New York in 1900. This is New York in 1920. Out with the horse, in with the Ford. Mass transit fueled by gasoline-powered engines opened up endless possibilities, economic and otherwise, and continues to do so to this day. But both the industrial and transit revolutions came with significant cost. They relied on the burning of greenhouse gas-emitting fossil fuels to power them both. Now, aside from pyromaniacs, most people don't burn things just for fun. They burn things like fossil fuels because they allow them to do something else they value: build a widget, or drive to work, or heat their homes. That is, carbon emissions are what economists call a negative externality, a cost associated with a private benefit that affects a third party who did not choose to incur that cost or benefit. In this case, the third party is all of us. And this is why combating climate change is going to be so difficult. It is the unintended result of the pursuit of ends, comfort, happiness, freedom of movement, and gainful employment that most of us agree are important. We have met the enemy, and the enemy is us. It would be comforting if we could blame all our problems on big oil and big agriculture, but to do so would be incredibly disingenuous. So, let's talk about global warming. First, the globe is warming. As this figure shows, NASA's Goddard Institute has data going back to 1884. 19 of the 20 warmest years on record have occurred since 2001. But that warming is not occurring linearly or evenly. Think, if you will, about the difference between cooking in an oven versus cooking over an open fire. There are a lot more variables in the latter scenario. The reason climate scientists have begun referring to the cumulative effects of greenhouse gas buildup as climate change rather than global warming is that the changes are much more pervasive than just warmer temperatures. We are seeing changes in the means and variances in precipitation, temperature, humidity, etc. that define our ecosystems. The old normal was that weather in a given region followed a normal distribution around a given mean. And remember, those means can be quite different. Normal weather in Denver is not normal weather in Monrovia or Cairo. Some days are hotter, some are cooler, and relatively few, out in the tail ends of the distribution, are much cooler or much hotter. Climate change is causing a change in the mean, a shift in the overall distribution, but also in the variance around the mean. Note that the new normal has more area in the tails in both directions. Global warming is not just making the average days hotter, it's making weather more extreme. If you were in Denver this past week, you experienced this firsthand. And it's not just temperature and precipitation. We're seeing related effects, largely due to ocean warming, that are making hurricanes and typhoons potentially more frequent, but definitely more devastating. Recent Intergovernmental Panel on Climate Change special reports on a 1.5 degree warming scenario, climate change and land use, and the oceans in the cryosphere being the frozen part of the Earth's water system, provide even stronger evidence of anthropogenic effects on the atmospheric, marine, and terrestrial systems that will have effects for changing land use patterns, ice melt, and urbanization, all contributing to warming dynamics at multiple spatial scales. From these most recent reports, several projections stand out as especially noteworthy. First, extreme once-in-a-century storm surges will be expected to occur yearly by mid-century. Storm surges are among the most devastating effects associated with cyclonic storms, which can have disastrous consequences for human security.
Powerful winds aren't the only deadly force during a hurricane. The greatest threat to life actually comes from the water, in the form of storm surge. Storm surge is water from the ocean that is pushed toward the shore by the force of the winds swirling around the hurricane. This advancing surge combines with the normal tides and can increase the water level by 30 feet or more. Storm surge combined with waves can cause extensive damage. It can severely erode beaches and coastal highways. The pounding waves can take out boats and buildings. As the waters move inland, rivers and lakes may be affected and add to the rising flood levels. While we can't prevent storm surge, we do have a system that can warn us of the incoming threat. As a hurricane develops over the open ocean, forecasters at the National Hurricane Center closely monitor its path to evaluate the risk of a coastal strike. They use a computer model called SLOSH to predict storm surge heights. The model depends critically on the hurricane's track, intensity, and size. SLOSH uses water depths, land elevations, and barriers to the flow of water to compute surges as they move inland. This data helps determine which areas may need to be evacuated. When a hurricane slams our coast, it's important to be aware of all the dangers. As a reminder, emergency managers want us to run from the water and hide from the wind. Don't take unnecessary risks during a storm. Conditions can change in the blink of an eye. Storm surge is a dangerous event during a hurricane, where furious winds are driving deadly flows of water from our seas to our shores.
Second, projected geographical shifts and decreases of global marine animal biomass and fish catch potential are much more pronounced by mid-century. This redistribution of resources in abundance significantly increases the risk of conflicts among fishing authorities and communities, which has been a significant source of global conflict in the past. And third, climate change can and will amplify environmentally induced migration, both within countries and across borders, with rapid onset extreme weather events and slow onset events both contributing to exacerbating stresses. Now, human societies have proven remarkably adaptable to different climates. This map shows the Earth broken down by Köppen-Geiger climate zones, a way of characterizing climate that assimilates a lot of information about temperature, patterns and levels of precipitation, humidity, and seasonality. Humans have managed to eke out an existence in some truly extreme environments, such as the Inuit and native peoples of the North Polar region to the various residents of the world's vast desert regions, and they've done so at least in part through physical adaptation. But the overwhelming majority of the adaptations that have allowed humans to thrive in such diverse environments have been technological and civilizational. How society is structured, what types of clothing and livelihood strategies are used, etc. And these adaptations occurred over centuries, if not millennia, creating what we will refer to as location-specific coupled natural and human systems, via which the environment affects human behavior and social organization, and vice versa. Climate change is radically altering the timescale over which adaptation will need to take place moving forward. Now remember this map. In class, we'll be using it and the IPCC report as the basis for a group exercise. So what areas of the globe will be most affected by climate change? Clearly, low-lying coastal areas will be impacted by sea level rise, with some entire countries, like the Maldives, whose cabinet held an underwater meeting to raise awareness about climate change, existentially threatened. These countries may no longer exist in the territorial sense later this century, But the effects are not limited to low-lying islands. The world's river deltas are some of the most densely populated places on Earth due to their agricultural productivity. Places like South Asia, parts of northeastern China, the Nile Delta in Egypt, and the eastern seaboard of the United States are obviously threatened as well. But it's not just these areas that will be affected. Agricultural productivity in the equatorial zone, the area between the tropics of Cancer and Capricorn, is expected to decrease dramatically in productivity due to warming and increasing aridity. By 2050, it's expected that vast swaths of the Earth will be experiencing much more water stress than they are at present due to a combination of lessened rainfall and increased demand due to population growth. We're also seeing an increase in extreme weather events and weather-related events like storms, wildfires, cyclones, and droughts. And those extreme events are increasingly linked to climate change. The 2014 IPCC report notes natural disasters such as floods, droughts, and hurricanes have become increasingly frequent and intense in the past several decades, and are likely to increase in intensity moving forward. And recent reports by the American Meteorological Society and the National Academy of Sciences have advanced the abilities of scientists to identify specific natural disasters, such as the 2017 Great Plains drought and the Southern European heat wave of the same year, that would not have occurred if it were not for anthropogenic climate change.
It's really cold out. And right on cue, Twitter has been overrun with climate deniers cracking tired jokes about global warming. But beyond social media jabs lies a serious and ongoing discussion about how scientists connect extreme weather, be it a cold snap, a hurricane, or California's extreme fire season, to underlying climate change. Because the truth is, this science is really new. The first proper climate attribution study was published in 2004. Before that, scientists had struggled to explain exactly how specific weather events were connected to climate change. Now, more and more solid, peer-reviewed studies show how climate change affects the likelihood and severity of extreme weather. And the studies are getting published really quickly after extreme weather events take place. Remember that study from 2004? It looked at a European heat wave that took place in 2003 and took a year and a half to complete. In contrast, just 3 months after Hurricane Harvey, scientists at Lawrence Berkeley National Laboratory published a study showing that Harvey dropped 38% more rain than it would have without underlying climate change. Another group, called World Weather Attribution, found that hurricanes that size have become 3 times more probable. Here's how Miles Allen, one of the authors of the first climate attribution study, explained why studies today are getting published so much faster.
When we performed the study in 2003 looking at the European heat wave, nobody had actually attempted to quantify the role of human influence on climate in a specific weather event. We are now looking at accelerating that whole process, because once you've agreed on the method you're using, you don't need to reinvent the wheel. The actual time it takes to actually do the calculations is not that long.
The developing science of attribution means scientists will have to completely reevaluate how they talk about extreme weather. Because terms like 500-year floods and 100-year droughts, terms that are supposed to indicate the frequency of a hazardous event, are becoming less and less helpful as frequencies keep changing. And it also means that in a few months, scientists should be able to explain the relationship between this cold snap and climate change. And projecting further into the future, it's entirely possible that we will soon hear scientists make these links as these events are happening.
We should be able to do this much faster, but in my view, in the long term, this should be part of the duties of the Weather Service. It's no longer enough for the Weather Service just to predict the weather. They should be in the business of explaining it as well.
While exact numbers are difficult to estimate due to the problems inherent with identifying a monocausal explanation for migration, natural disasters and environmental changes such as rising sea levels may displace up to 1 billion people, both within countries and across international borders, by 2050. So, to recap the main points from this lecture. 1. Climate affects weather, but weather is not the same as climate. 2. Global warming is occurring, and it's occurring due to the greenhouse effect, and has really taken off since the industrial and transportation revolutions. 3. It's changing not just in terms of climatic means, but also variances around those means, leading to more extreme weather events. And 4, the effects will be pervasive, affecting every region of the globe, but particularly negative for low-lying coastal areas and areas close to the equator. Next time, we'll broach the concept of coupled natural and human systems, which will help us to think systematically about the ways humans interact with, indeed shape, and are shaped by, our environment.